I'm Arif Masud from University of Illinois. And as Jake mentioned, I'm going to talk about advanced methods, computational methods for blood artery interaction in patient-specific geometries. And Jake is one of my collaborators in this work. And Soon-Pil Kang, he's a current PhD student who's working with me on this particular topic. I will present an overview also of the work that we have done with the current Blue Waters allocations that we got and the earlier allocations that we have received in the form of the research highlights. But before we go in there, question is, what is the challenge in here and why Blue Waters? And as I mentioned, that we are interested in developing techniques that can be applied to patient-specific models so that we can do either patient-specific diagnostics, or we can use numerical techniques or computational methods for planning, vascular surgical planning, and patient-specific treatments. So that brings in the question that real-time data, real data, patient-specific data needs to be embedded in high-fidelity computations, which means that the mathematical models and methods that we are developing need to be not simplistic, rather they should be physically based, they should have the physics in it, and that brings in the complexity. Because in addition to the uncertainty in the material parameters, there is uncertainty in the sense that biological systems lead to mathematical frameworks that are that have reduced stability. They are not very well defined. They are not very well described. So question is, how can we bring patient-specific data in high-fidelity computations for the class of problems that we see in clinical applications? So with this in view, we have paid a lot of attention. We have put a lot of effort in new method development, new model development. I'm going to show today computations with shear rate dependent flows, where the constitutive model is more involved than the typical flow models that we see in civil, mechanical, or aerospace engineering systems. And we have specifically developed this new class of models, generalized all-right B models, viscoelastic models for blood flow. And we have published papers on this particular topic. And we have also developed new class of stabilized finite element methods, and I'll qualify this word stabilized finite element methods for non-Newtonian fluids and for the class of fluid mechanics problems that we see in fluid dynamics. Unlike, as I said, in civil or mechanical or aerospace applications where flow is uniformly coming on, here is a stop and go. And this gives a lot of beating to the numerical technique that you're developing. And I'll show some applications. We have applied this method to continuous flow ventricular assist devices in the case of, and the effect of that on carotid artery and the propensity of coagulation, which can give rise to clot formation that can give rise to stroke. We have also applied to blood artery interaction models, and this is where I'll put my most of the emphasis, as this is what is new that I'm presenting here that has not been done by us, at least previously, and what is new in here from the perspective of mechanics as the community. And we are also, I'm going to present an issue of high gravitational accelerations, high G's, we call it G-lock. G-lock is loss of consciousness under high gravitational forces, a problem that all the combat pilots face. So this is a defense type application as well. But if you have ever been on a roller coaster, and a roller coaster is, let's say, on the average higher than 400 feet, then it can produce 3 Gs, which is same as what a combat pilot feels. And I will present what kind of feelings can you have, or why what you feel is, what is the physiological basis of that. Along the way, I've also had the opportunity to work with some of the undergrads who got the Blue Waters allocations, Blue Waters Fellowship, and also some undergrads that were funded by National Science Foundation. And these students work with my graduate students to write Java and Python codes so that we can extract patient-specific information from MRI and CT scans so that models are as accurate and robust as possible. And they wrote codes for processing patient data for 3D printing. So we can take the geometry and we can print it out. So simulations that we do, we can also print those out. And my collaborators have been Professor Bill Grob from University of Illinois. He helped us figure out what are the bottlenecks for codes that are implicit, are PDE-based approach, but implicit calculations, and how can we overcome those issues. Mark Venmore from NCSA helped us in developing some of the graphics that I'm going to show here. And Dr. Geeta Bhatt from Heart Institute of Chicago, she has been collaborating with us and providing all the patient-specific data. And this is also not an easy thing to do, because getting patient-specific data has a lot of bottlenecks along the way. So now coming back to the model, this plot here shows the viscosity versus shear rate. And as I mentioned, that blood has a tendency to coagulate. And if you don't shake it well, if it is not shaken, its viscosity increases. And lucky for us, that heartbeat gives stop and go type thing, so a lot of shaking. And because of that, its viscosity decreases, and so we don't have the issues. However, most of the time, we are in this range, so our shear rate goes up and down, and viscosity varies considerably. And this can be contrasted with typical fluids, air or water or oil, where viscosity is considered to be assumed to be a constant. So shear stress and shear rate is also nonlinear, in addition to the nonlinearities that are coming in because of the equations. So here is the system of equations, our model. This is our momentum balance equation, incompressibility, velocity boundary conditions, stress boundary conditions, and initial conditions. And in addition to the nonlinearity that is induced by this nonlinear term here, the stress is also a nonlinear function of strain rate, because viscosity is a function of shear rate, and shear rate is dependent on rate of deformation. So now we are adding more nonlinearity, but that is what the physics is if we want to model it correctly. And that brings in another layer of complexity in our computational systems. If we develop the standard weak form, standard Glerkin form, that is the basis of developing the numerical method and also the finite element method, it looks something like this. In order to be able to develop techniques that will give us physics, relevant physics, without having instability issues in our calculations, we need to pay special attention to this nonlinear term, and we also have to pay attention now, for this particular case, to the stress tensor, which is highly nonlinear as well. So degree of nonlinearity or degree of complexity of this model is a lot more. Now, there are different techniques that have been proposed in the literature to address this kind of problems. However, I will talk about some techniques that we have developed at University of Illinois, and also highlight the role of blue waters that has played for us to develop these methods. Any numerical method, finite difference, finite volume, finite elements, any method, as we make a mesh, as we discretize the domain, the mesh starts behaving like a filter. It is able to capture physics which is larger than the characteristic length scale of the mesh, which is the size of the element. And all the features in the physical features that are smaller than the size are dropped out. Okay, so we define the mesh. We define the mesh, we get better physics. But we can keep on doing, and we can define the mesh, and we see that if we keep this line of argument, then very soon we can exhaust any computational platform. So the question to ask is it possible that we can live with cruder discretizations and can somehow model the features in the flow that are smaller than the size of the element? So now, think of the total solution. With a good method, let's say if we can capture total exact solution, a part of it can be captured with a good method, a part is filtered out. So what is filtered out is in fact the error, and error is also a solution to the problem. So with this mindset, we say we can split the total solution into coarse scales that we can capture and fine scales with that filtered out. And here what we have developed is we have developed techniques that can capture this coarse scales and model fine scales. And that is the new contributions that we have done in our numerical methods here. We split the total solution into coarse and fine. Weighting function is arbitrary function, so it can also always be split into coarse and fine scales. Whether this is linear or nonlinear, weighting is linear. So we can substitute this additive split form of the solution and its weighting function in the weak form, Glerkin form that I showed, and that gives rise to employing the linearity of the weighting function slot. Again, problem could be linear or could be nonlinear, solid mechanics or fluid mechanics, its weighting function slot is always linear, and that helps us split the problem into a coarse scale problem and a fine scale problem. And there is some mathematics in here because of, for time, interest of time, I am skipping that. So here it is, the whole system. So we have coarse and fine scale weighting function, and in the solution slot, we have coarse and fine scale velocity field. Employing the linearity of the weighting function slot, we can split this problem into a coarse scale problem and a fine scale problem. And that fine scale problem provides us a mathematical and a computational microscope. we can, now objective at that point becomes, solve the fine scale problem, and we can solve it either over an element or a patch of element. It can be our choice, and I can talk about that. Find the solution of the fine scales, find a representation of the fine scales, and so that we can embed that into the coarse scale problem. And when we solve for the coarse scales, the fine scale physics is mathematically embedded. Now, for relatively simpler problems, we can split, we can find some analytical solutions, we can find analytical tools, but for highly nonlinear problems, we need to do some computations, which means, let's say, if we were doing this at the element level, and in all the simulations that I'm going to show you, they are done at the element level, it's not only highly parallelizable, it is also, it's a process that helps us make the element smarter. So substituting that, we get this form of the equations, where we have, this is exactly what is there in the Glerkin form. The black terms are the Glerkin terms. These are the terms that have appeared. They represent the effects of fine scales which are otherwise filtered out. We call them stabilizing terms. And in these stabilizing terms, we have these two terms that have now appeared for the case of non-Newtonian fluids, and they are representing the effects of the fine scale viscosity evolution. As I mentioned, that these give rise to, so these are additional terms that contribute to the stabilization, and these terms are important for obtaining optimal convergence and solutions that are physics-based. So a lot of our effort has been on developing these methods. We had to run multiple simulations, simultaneous simulations. There are large simulations and need to be run simultaneously to be able to figure out the development of the method and also quantify the uncertainty in the coefficients. Now, a little bit about the code. We use mesh partitioning using ghost node technique, Metis library to partition the system. We get balanced load, but this is still an issue that we are confronted with, unbalanced communication patterns that we are still trying to help improve. PETC is used to solve the system of equations. As I mentioned, these systems have borderline stability, so we have developed implicit methods, and we use Newton type strategy to solve it, generalized alpha method to solve this time-dependent system of equations. And since most of these computations are done at the element level to make the element smart, so that coarse mesh can give us same accuracy, which otherwise a very fine mesh will give, we are already addressing the issue of message passing because we are minimizing the communication, the cost of communication for real large-scale problems. So here is the speed up versus number of processors. We used a typical problem, turbulent flow problem, 32 cubed mesh and a very fine mesh. And for 32 cubed mesh, we see the scalability going off because of the number of ghost nodes increasing. But as the mesh sizes increase, as the problem is made more intense, larger, we get this scalability as shown in here. So the number of ghost nodes for smaller problems reduces the scalability of this system. Now I'm going to show you some applications. Here is the case of carotid artery, which is this artery over here, and I'll show you some numerical simulations in this particular case. These were done with our pre-allocations that we got from Blue Waters. Here is a numerical simulation where we have a diseased artery. You can see this constriction in here, and you can see this ballooning effect in here. Ballooning effect, aneurysm, and stenosis. And you see this pulse, so this green line shows where we are during a typical heartbeat cycle, and as you see, it goes through the peak here, systole. There is a jet effect that comes in, and it breaks. So you see this jet effect. There are two issues. One is that this jet effect can cause some problems here. If your endothelial layer disrupts at that point, body's natural mechanism kicks in, and it tries to repair it. But in trying to repair it, it can produce a clot that can move on. In addition, if you see here, as the jet action comes in, this disrupts this buildup of this red, but as we go past in the diastole, this red region increases. Red represents increase in viscosity. So there is a time for every heartbeat cycle where blood has a little bit of time to sit there, its viscosity increases, and next beat comes in and pushes it forward. But this is susceptible. This becomes high-risk situation for the patient. Here are different snapshots of the different time points. This is at the time when we are here, and we see considerable buildup of viscosity. If you have a constant viscosity model, it will not be able to predict that. It will not be able to predict the risk for the patient. I'm going to show you another one. This is Newtonian flow. Newtonian flow viscosity is constant. There is no change in color. The current model that we are using, the color shades here show build-up of the viscosity, and you can see that in this aneurysm region, which is the diseased part of the artery, viscosity increases, and then the heartbeat comes in, and it moves it forward. So if you take the difference of the two, difference is considerably higher exactly at where the disease exists. So this kind of technique can be used to identify regions and the risk for the patient. And now let's look at the two different situations. The maximum difference in the case when you are at the peak is 4%. It looks like it's a small difference, but it is at the peak. Difference is everywhere along the way, and if you integrate it, it's quite a bit of difference. The next is, at this particular point, end of diastoling, and Newtonian. This is, we have projected the stress field, and the difference is 16%, okay? So here, difference is pronounced, but also take a look at that the portion of the peak cycle is 20% of the entire cycle. So 80% of the time, we are predicting stresses which are 16% less than what they are. It is on the non-conservative side. So unless we use numerical methods which are high fidelity, and not only that, high physics models, we cannot use these techniques for diagnostics because we will be under-predicting the stresses. Stresses in the patients are higher, and we are not able to predict it. Risk factor is high. We are on the non-conservative side. Another thing, now I'll talk about 3 items that we did in the last year and a half. One is flow assisted heart conditions. So this is a flow device. There are different types of devices, artificial heart pumps, you can say. Some of them beat, and they try to mimic the behavior, how the natural heart beats. However, because of fatigue effects, their failure rate is higher. Another one is continuous flow devices. It's like a pipe with a spiral spinning inside, suspended and spinning inside. So there is, beating effect is less. So their durability, engineering durability is better. But I will talk about what happens. Flow is now continuous flow. It has lost its beating. So when we put it in a patient, the body organs are getting the same volume of blood, but not the beating effect. What does that mean? So continuous flow WAD devices, although they are very popular, and we were on this one, we are working with the Heart Institute in Chicago. Issue is that some patients come back because of formation of clots a few months down the road. Device has longer life, patients are having some issues. So we looked at, purely from a computational point of view, this is a healthy heart, and you see this region where the viscosity builds up and the pulse comes in and disrupts it, even for a patient with this disease condition, and the coagulation is disrupted. This is the condition of continuous flow. There is flow going on through this artery, but there is a standing wave, which means that there is a pocket where blood can come in, thicken, and then move forward. You can think of it as milk and yogurt. Yogurt is thicker. So there is some thickness in here, and then this blob of yogurt moves together with the blood. Chances of risk become very, very high. Thank you. And then we said, we don't want to give the same pulsatility because then it is going to get the heart, artificial heart, the pump is going to get a lot of beating. What is the minimum pulsatility, and what should be the amplitude? And through numerical computations, and here we had to do multiple computations to be able to figure out, span the space of uncertainty in terms of material parameters to get the representative scenarios. And so here is 10% of pulsatility is just enough to disrupt that build-up of the viscosity, and that should work for the patient. So we can use these techniques for patient-specific treatment or patient-specific adjustment of the artificial heart. So you can think of it as numerical techniques for help in operation or optimizing the device for the patient. Now, another thing that I want to highlight is flow structure interaction. I talked about the fluid domain, the complexity of the computational model. Now the blood-artery interaction. So artery is also viscoelastic. It's not simple elastic. Viscoelastic models are more complex than pure elastic models. And in addition, we have developed this fluid structure interaction capability where both the fluid and the solid domain are fluid and the solid domain are solved in a coupled fashion. Here is the big flow chart of the structure of the code. And what we have done is we use monolithic approach. People have used staggered approaches. Reason, because when you stagger, your systems are smaller, And therefore, you can use a platform which may not have as much compute capacity. You can use it for this class of problems. Restriction, you are first order accurate for highly nonlinear problems. And long time calculations with first order accurate methods is not a good news. Most of the time, you can get results which are non-physical. You cannot compare it with the data. So you need at least second order accurate methods, for which you need to go to monolithic schemes, which means fully covered. There is where Blue Waters comes in. It provides us that large platform that we could try, implement, and run this class of problems on larger platforms. And it turns out that these methods are highly stable, and I will show you some numerical results. We looked at the case of, I will show different cases, young and healthy versus old and calcified. If the geometry is kept the same, the flow properties are kept the same. Now the artery properties are varied. Young people, elastic systems. With age, you develop calcification, so arteries stiffen. This is a natural phenomena. How can we bring it into our calculations? And we figured out that if we look at a model which considers the artery to be elastic, and elastic means that relaxation time is 0, versus viscoelastic models with two different relaxation constants, so there is some variability in there, and that is where we needed to do multiple simultaneous calculations. If that be the situation, what happens? So here is one simulation where we have shown here the instantaneous velocity magnitude at different cross sections. Looks like that these are good simulations. And in this portion where there is disease, we see a lot of disruption. Actually, nature built things to be as smooth disks as the flow in these disks over here. Because of this disease condition, there's a lot of disruption. However, if you look at these numerical results, this black line is the inflow velocity at this point, and the red and the blue are the outflow velocity at the internal and the external carotid artery. If you look at the pattern of this is the internal carotid artery, this red line in here, you see that this pattern is completely different. In a small portion of length, the pattern cannot change, should not change. That is the pulse, that is your natural. So we developed the model for viscoelastic, and I'll show you the results for viscoelastic, more intense model, heavier computations. Physics appears the same. What is more important here is that the pattern is maintained. This is one of the, I'll just wind up. This is one of the proofs that in order to get relevant, clinically relevant, physically relevant solutions, we need to go to models with high fidelity. Here is the case of just the blood flow in case your artery doesn't move. This is shown by this dotted line. And then we have plotted on top of that the solution for the case where we have relaxation time. Blue is relaxation time of 0, which means elastic, and red and green are viscoelastic. And you can see that the red and green are more close together, and the blue is different. From here, we can compute the difference between the soft and stiff arteries. It turns out to be 20%. So with this kind of techniques, we can look at the propensity of hypertension in a patient. So if there is a patient for which we have kept track of with age, kept track of the mechanical material properties in terms of viscosity of the blood, and also the density and the mechanical properties of the artery walls, with time, we can predict their chances of developing this issue of hypertension. And last problem that I'll show in a couple of minutes is this problem of G-lock. G-lock is loss of consciousness under high gravity conditions. This, as I mentioned, fighter pilots are always confronted with this issue, but as I mentioned, the general public is also confronted with this issue. If you go to an amusement park and you go into a roller coaster that has a drop more than 400 feet, and now these days, a lot of roller coasters are coming in, what happens is that there's a point in the middle, somewhere here in the body, which is net neutral. And if you are, so you can feel gravitational force in the X, Y, or Z direction. Let's focus on the Z direction. If the body is moved too fast in the Z direction, it causes the blood to start moving downstreams from this point rather than moving up. So your blood perfusion in the brain is reduced, and blood pressure also reduced. But in order to be able to model this problem, we needed to develop what's called the boundary conditions, because you cannot just take a portion of the body and do blood flow analysis, because it is continuous, fully connected. So what are the right boundary conditions? They simulate or they reflect the portion of the body that you are not accounting for. So we needed to develop these boundary conditions. This is a paper that has appeared now, and with that time-dependent boundary conditions, we are showing you here that results for the full geometry. Again, we could do the full geometry because of blue waters. And then using that as a reference point, we developed the boundary conditions that now replicate. Now we can solve for, we can go surgically, sort of numerically, surgically go and do calculations on a small portion by applying these boundary conditions, and we do not have to solve for the entire system. This was also only possible because of blue waters, because we could solve the entire geometry. And here are the two different cases of stenosed and non-stenosed artery. This is where we want to go related to the whole thing. This shows the mesh that we have computed on. This is just the outline. We have different density meshes. This shows the instantaneous profile of the pressure, and this is what I want to bring to. This is 1G. So we have picked out two arteries here, number 1 and number 2. Outlet 1 is here, outlet 2 is here. Look at outlet number 2. And at 1G, this is the flow rate. When it goes to 3G or 5G, flow rate has reduced to half. If it is 3G, which you feel on the roller coaster, the flow of blood to your brain has reduced by 25%. Here is the pressure profile. At these two sections, we are looking at the pressure profile at 1G, which is so normalized with respect to 1G under normal conditions. This is exactly where it is. If you are in a 3G situation, your pressure has dropped by 35%. That is why you feel, this is a physiological aspect of blood flow affecting or dizziness. People feel dizziness. These are instantaneous, not snapshots. One last line, where do I see this thing going? We have developed blood-artery interaction model, large deformations, but they are not that large. Issue comes in when we want to develop numerical techniques to do replacement of the heart valve. And these days, there are lots of procedures. So procedures are already there. People are using artificial heart valves. Cardiologists are inserting them through the stenting procedure. However, at that point, we need to account for the calcification so that we do not inflate it. So we break the calcification that can cause clot. And if we do not want to not inflate it enough, because then there will be issue of backflow. So this now needs very sophisticated object interaction problem where heart is always moving, large deformations, and we need to be able to very precisely figure out, and this has to be patient specific because every patient has different calcification of the domain. So this is where we think, or I personally foresee that this numerical technique can be really beneficial for surgical planning, which is very, very critical. And as a matter of fact, these days, if you talk to surgeons, especially that do heart valve replacement, they tell you that they get a lot of CT scans, and after looking at all those CT scans, they have an idea. But here you can actually look at what should be the pressure and what should be the variation and should not go beyond that point. With that, I would say, we have showed you some non-Newtonian models, new methods and patient-specific outflow conditions. This was one of the important things that we were able to develop in this year. I've shown you in the case of hypertension, we can model, in this case that I showed you, that particular case, there was 20% high pulse pressure. And we also are looking at intracranial hemodynamics and its effects on consciousness. And publications. And finally, I will want to again thank Blue Waters and NSF for their support of this work. Thank you.
Thank you, Arif. It's a great talk. Any question? We have several minutes before lunch.
Yeah, I was wondering, so when you're talking about stability, I'm trying to figure out exactly what it is that you mean. So you said that the nonlinear terms make it stable. Is that correct?
No.
That's why I was confused.
Yeah. Stability. In mathematical models, there are two types of stabilities. One is two types of instabilities. If it is numerical instability, which can come in because of the v dot grad v term, the skew term, then you need to develop a method to be able to address it if it is numerical instability. There is another kind of instability which is coming, which is telling you something about the system. If it is system-based instability, material is becoming unstable at that point. Material is fluctuating. The artery is just at that critical value and the artery wall is fluctuating. Then you need to develop a method to be able to follow it. You cannot suppress that, otherwise you're suppressing physics. So there is one, what is called mathematical instability. Develop techniques to suppress that. And there are stabilized methods that have been developed to address that. In our case, we have developed these methods based on what is called variational multiscale that provides you an ability to develop a fine-scale mathematical model and therefore not just simply add, for example, an artificial viscosity, which most of the fluid mechanics models do. Here, the fine scales are driven by, here I could not show you the details of that, but we have published enough papers on that. The fine scales are in fact proportional to the residual of the Euler-Lagrange equations of the coarse scales. So now the point is that if, let's say, you reduce the inflow velocity such that the flow becomes from turbulent regime, it comes to steady state, it becomes laminar flow, and your mesh is good enough for resolving that physics, then in that case, if you had put an artificial viscosity, that viscosity is always going to sit there. But if your fine scale terms, fine scale fluctuations are proportional to the residuals will disappear, and these terms will automatically, their effect will disappear. So it is residual-based stabilization of the method.
I see. So in order to do these equations, my understanding is that normally you have to do like an iterative method. Is that not the case here?
Absolutely. It is iterative method. As I mentioned, it is Newton method.
Oh, right.
Yeah.
Okay. All right. Thank you.
I was wondering if, are there any kind of, you're talking about patient-specific geometries,
right.
And are there any kind of repositories that, I'm not very familiar with the field, but are there any repositories that would have kind of the results of these simulations given a patient-specific geometry? I'm guessing like some geometries will lead to a higher probability of, some kind of medical problem in the future, and others are, you can consider them as
right. If I understand your question is that, because if we make a mesh which is engineered mesh, we know the diameters and everything, and anybody can reproduce those meshes and compare the results, let's say, with these calculations. But if they're patient-specific and your geometry is not fully represented, then local effects in the change in the geometry will affect the physics, and you cannot do a point-by-point, let's say, comparison. If that is the case, there are only a handful of these repositories out there. The flow that I showed you on stenosed artery, that is available on the web. That is available, and for that, yes, you can. But typically, if you look at the blood flow mechanics papers, there are hundreds of papers that are coming out. Each one is using one specific patient, but that patient is different from some other patient. And as you change from one to the other, these local geometric changes affect the flow locally, and therefore not having one common, let's say, test bed has been a serious problem for validating biofluid dynamics problems. So it's a very valid question. And actually, in order to address that, when we wrote this paper, we wrote another paper in which we developed bifurcating arteries with different diameters, which were geometric. Geometric means that we could define the parameters and we define the geometry so that people can use that as a reference and compare with their method with our method on that geometry for which there is no ambiguity. Patient-specific needs a lot more. We are dealing with this Heart Institute in Chicago, and I can tell you that getting patient-specific data is not easy at all. There are so many signatures that you have to get done, and still, at the end of the day, there are certain computations that you do that we still give to the Heart Institute, but we are not supposed to publish. Okay? So I think this is a very good question, and someday biofluid dynamics community will have to address it. Because otherwise, how would you justify which method is better than the other?
Okay, thank you.
Okay, so Last question.
My first question is that how confident is the Young modulus that you apply for the FSI and the mechanical properties of the stiffness, like the strength of these tissues and the model that you use in your FSI, and is it a kind of linear material or not? And for the first part of your talk, if the viscosity is highly dependent on both velocity of the flow and also the density that it accumulates. So if, the expansion of artery is so big that it can just mediate that a bit, can you comment on that?
Yeah. So your question is two parts. One is how confident we are about the mechanical material properties that we used in the arteries. There have been some studies that were conducted in 70s, 80s, and 90s by NIH, and in which they took thousands of patients or subjects, and they grouped them into, let's say, male and female separate. Amongst male, 20 to 30, 30 to 40, 40 to 50 group. And then they have published some distributions. So these coefficients were taken out of those distributions. It's representative of a Young. So we skipped the middle because the 20 to 30, your arteries are hopefully in pretty good condition, and at a later stage when calcification is a natural process, nobody can avoid it. So we took these two cases so that because we could run only as many of them, so we skipped the middle portion. So we took these two cases, and from their distribution charts, we picked the representative values. So NIH has done extensive study on that, and these studies are used by doctors when they want to classify things. What was your second question? Yeah. Second question is, yes, the local features in the flow model, they are a function, viscosity is a function of the shear rate. And if the artery wall is moving, then shear rate would be different as the shear rate of a fixed artery. That is exactly what I was trying to say. That if the artery walls don't move, then you can think of it as flow in pipes that mechanical engineers have been doing for a long time, short of having the shear rate dependent flow, even with the artery walls not moving. But if the artery walls are moving, then your local flow features are different. These calculations are fully accounting for all those effects. But what does it mean? It means that your flow models are more complicated. Your flow structure interaction can bring in some instabilities. And therefore, and that is where I was saying that we need implicit methods, because implicit methods try to solve the system of equations at every step, whereas if you're using explicit methods, they are only projecting from step n to n plus 1, n plus 1 to n plus 2. And when you say, well, you have not solved the system of equations, are you sure about these results? Answer is yes, because at time t0 we started with a system that was which was stable, self-equilibrated. So as we are projecting n to n plus 1 to n plus 2 to n plus 3, and since our projections in time are only very small, so it should be. Should be doesn't work in biofluid dynamics because of the complexity of the flow that we involve here. So we had to go ahead and develop implicit methods, and it took us a lot of effort to do that.
So you present a lot of research progress. So what is the most important result done by your science team this year, and what is your next goal next year?
Well, I would say the most significant was blood-artery interaction. We showed that if you have a fully coupled system, you can get quadratic convergence rates. This is an important thing, and even then, even when you can show quadratic convergence rates, you can still come up with a class of problems where you just increase the nonlinearity further and you start losing it, okay? So I think that is an area which can have a profound impact on computations as we do today. Coupled field problems. How do you develop coupled field problems for problems which are in fact highly nonlinear? So one of those things I would say. And the other thing is that blood artery model is right now an excuse to develop something more involved, because eventually we want to be able to use it, let's say, for vascular surgery, vascular surgical planning. That is the goal. But in order to be able to get that, these problems are building blocks. Now, in case of a heart valve which is not functioning proper, heart valve is calcified, so you cannot take the model that you got or data or statistical data from one patient and say, okay, statistically this should work. No, it doesn't take place like that. There's so much of variability from patient to patient, and the same patient over the years, that in future, in time to come, as we say, patient-specific treatment Computational techniques will come in to provide you patient-specific, but for that, you will need to keep track of, as you go and meet the doctor, they'll keep track of those information, and someday, computations will be at a point that based on previous data, they'll be able to project what kind of issues you can face. If we want to do that, then these methods need to be further taken, not only from a computer science point of view, how large a problem can you run, but also from a mathematical point of view, that system which is stable now, you can make it unstable by making more complex. Natural problems is more complex. You take a patient with this heart valve and ask them to walk. Conditions will change within a minute. So that is where complexity arises.